all sorts of fun stuff. So there we go. Oh. .214 is different from .213. .213 is very visual. You have Atwood's machines, you have things sliding down incline planes, you have merry-go-rounds rotating. You could see this stuff. With .214, it's very cerebral. Oh, and the other thing, I'm not bothered by the fact that we have canceled class on the 3rd. The university basically told us to make up that time, either extend class by a few minutes every day or pull your break, don't have break. And since we never have break anyway, it doesn't really matter for us. .214 is very cerebral. It's very, you're gonna have to visualize things. We're gonna be talking about electric and magnetic fields. You just can't see an electromagnetic field, so you're just gonna have to kind of think of your own way to think about it. Today in lab, I think it's lab 13, but it's at least the first lab. You'll be studying electrostatics. Now, for the first part of the class, we won't be jumping into the deep end of math, probably starting in the second hour. But electrostatics is the most non-mathy part of the whole semester. You're going to be given various bits of equipment, and then you got to describe what happens. The first thing that you do is you take an ebonite rod and rub it on rabbit fur. And I guess the rabbits all died of natural causes and donated their fur to science or whatever. I don't like to think about it. But the ebonite rod is kind of a plastic-like substance. And when you rub, what you notice is that when you rub the rabbit fur on the ebonite gains a particular quality about it. And what's happening is, in electrostatics, charges move. We've all walked across a carpet, like in the wintertime when the heat's on and the humidity is low. And you touch the doorknob and you get shocked. This is the same thing. What's happening is that the ebonite rod is rubbing up against the rabbit fur, and what's happening are electrons are coming off the rabbit fur onto the ebonite. So the electrons are rubbed off the fur. And this is just because of the way that the materials rub up against each other. Now, the charges move, and the thing that we need to remember is that the electrons, which are the negative particles, are the only ones to move. So the electrons move from the rabbit fur to the ebonite, and what happens is you get an ebonite rod where there is an electric charge all over it, kind of like a smear, dusting of electric charge. There is another type of interaction that you're going to have, and that is a glass rod with silk. And when you rub silk on the glass rod, what happens is that the electrons come off the rod. And what you're left with is a glass rod that is positively charged. So glass rods when rubbed with silk become positive. Ebonite rods when rubbed with rabbit fur become negatively charged. Now, the glass rod did not rip positive charges off the silk. The silk rubbed the electrons off the rod. So when I say something is negatively charged in this electrostatics part, negatively charged means excess of electrons. Hey. You want to talk?
I can do it now, I can do it later.
Like right now? Or you can talk to the class.
Okay.
Yeah.
3 of you got kicked out of section 3 for lab yesterday. Who was that? Where you at? Yeah, there were only 3 of you registered. Fortunately, 3 is not enough to justify having a section of lab.
Yeah.
So Martindale forced us to close it. So when you're done here, talk to Amy, who's in 104. They're set up in the tutoring room right now because the office is being renovated. Dr. Eschenberg, whoever you need to, we'll get it figured out. We'll get you in one of the other 2 sections. I think there are a couple seats open in maybe the
3 o'clock has space.
It has 2 seats open, and one of the sections is going to get 25 students. So
Yeah.
fortunately, since 7 other people didn't want to switch, instead of having sections of 15 that are going to move really fast, those sections are going to have 25, and you're probably all going to be there all day, every day.
We had about 5 people drop out yesterday.
Oh, we did?
Yeah. So you may want to look at those.
I looked as of last night.
Okay, that may be
there's
right.
currently 2 open seats in the labs.
Okay. So yeah, after class, talk to us and we'll straighten it out.
Yes, we'll get it sorted out.
But be sure to go to a lab today.
Yes, we're doing the electrostatics lab today. You need to be there.
We're kind of going over. All right. Do
what?
Oh, I thought someone had a question.
Oh, no.
Oh, it was just a snarky comment then. Okay, fine. So the negatively charged particles are the things that move. Negatively charged has excess of electrons. Positively charged has deficit of electrons. So when you have a positive charged object, there are missing electrons. When you have a negatively charged object, you have a surplus of electrons. So surplus or deficit. It's not these objects do not change their positiveness, as in number of protons on them. Now, charges can be transferred in one of 2 ways. There is conduction and induction. In conduction, there is touching. In induction, there is no touching. When you rub, now granted, when you rub the rabbit fur onto the ebonite rod, that's conduction. You are transferring charge through physical contact. In induction, there is no touching to move charge. We're going to go over both of these. In the lab, you're going to have something called an electroscope. That electroscope is a metal box. It has glass on the front and the back of the box. You'll notice that there's like a little plastic bead. That bead is non-conducting. And there is a hole at the center of the bead, and through the center of the hole is a metal rod. At the top of the metal rod, there's this big metallic ball. Down the length of the rod, they have a small sheet of gold, actual gold. Now, the gold is very light. It's pounded very thin and it has only a small area. It's probably worth like 20 cents. So don't think you're gonna steal that sliver of gold and then, I don't know, head to Vegas or something. It's not worth much. But this is a solid rod. The gold leaf is attached at one end and the rest is allowed to hang there. The first thing you're gonna do is you're gonna take that electroscope, the electroscope and the ebonite rod that is negatively charged, and touch. And when that negatively rod touches the electroscope, electrons are gonna jump from the from the rod onto this rod of the electroscope and then down into the main shaft and the gold leaf. And what's gonna happen is once you pull that rod away, there is going to be an excess of electrons. And that gold leaf will extend outward at an angle. So you know that there is a definite charge here because like charges repulse, unlike charges attract. So this is the simple thing with, this is charging negatively with conduction. So when they say charge negatively with conduction, you're going to take an ebonite rod, rub it with rabbit fur, touch the tip of the electroscope. As just a general comment for this lab, water is a dipole. It has a positive end and a negative end. So that stuff's charged. And in very humid air, there's a whole bunch of just water molecules flying around. What they're working on, Daniel, after he left, one of the things that he better had set up in that lab, they're gonna crank the air down low to get the moisture level down, and then they've got a dehumidifier in there to suck out more water. And they're gonna try to get it as dry as physically possible. Because when you're doing these experiments, the water molecules are attracted to the electroscope and they'll just start jumping onto the ebonite rod and the electroscope, and it reduces the effects of the experiment. The best time to do this experiment is in January, when we normally have it. Very dry air, very easy to dehumidify, versus today. Today's the worst day to have it because it's a very hot day, very humid day, and so to get that to work. So the ebonite rod part, that thing will charge up fairly well. The glass rod is a little bit more touchy. Because really what you're doing with the glass rod is when that glass rod hits the electroscope, the negative charges see a big positive area and they will jump onto that glass rod. So that when you pull it away, there is a net gain in positive charge, and you will see that leaf going on again. And so this is charging positively with conduction. And a lot of times, in order to get the real true effect, it's I think of the electrons or lack of electrons as kind of like a fluff at the end of the rod. You're going to actually have, when you touch it, it's a lot of times it's not going to be as simple as just going tap. You're just going to have to, like, if this is the electroscope and this is the rod, you're going to have to like kind of rub it around on the sides and stuff to make sure that the charges transfer. The other type of charging is charging by induction. Now, in a way, it's a little bit of a, it's not technically induction because the actual charging part is, does involve conduction. But in the first part, what you do is you get that negative rod close to, but not touching the electroscope. Now, there are free range electrons just hanging out on this electroscope, and negative charges are repulsed by other negative charges. So these negative charges will basically jump to the backside of the ball and down the rod into the gold foil. And so when you get that induction part close to there, the leaves will actually separate. And what those electrons are is that they were originally in the tip of the electroscope. But this side is negative, that whole bottom is negative, and this is positive. Now this is the conduction part of the experiment. What you're going to do, so this induces charged regions. So if I had, like, if you could think of this table as having just a bunch of electrons lying on the surface of the table, and my arm was extremely negative. I mean, I know I'm a negative person, but let's just say it charged negatively. The electrons at the surface of the table go, oh my goodness, what is this thing doing? And will shoot down the table legs. And so what I've done here is my hand is negative, the electrons in the table have shot down, which leaves a deficit of electrons in the tabletop. Now the net charge of the whole table is 0, but by taking a massively negatively charged object and bringing it close to it, I've induced charge, and this is the induction part of the experiment. But to get this thing to stick and remain charged, you take your finger, which is a neutral object, neutral as in having equal portions of positive and negative charge. But you're going to touch not the end facing the rod. You're going to touch the end on the opposite side of the rod, the back end of the electroscope, which is negative. And what happens when negative charges come in contact with the neutral object? Those electrons jump off. The electrons are stripped off. And then when you take your finger away, what you end up with is a deficit of charge. You've effectively stripped off. You've stripped off the negative charge of the electroscope with your finger and the negatively charged ebonite rod. So this is charging positively with induction. Now technically, this is the charging through induction. The actual touching with your finger is conduction. So to make it permanent, you're going to have to add your finger, which technically doesn't make it pure induction, but that's what we do. In the second part of the experiment, you've got the glass rod. And the electroscope, what happens in this case is that the electrons see that positive part, and they will all, not all, but a massive amount of those electrons will go to that side and hang out over there. When you bring your finger next to it, once again, your finger is neutral, has equal portions of negative and positive charges. And what happens when a neutral object touches a positively charged object? Think about, it's going to take the electrons from your finger. Because on your finger, there are equal number of positive and negative charges. That's what the definition of neutral is. So when you touch a largely positive area with your neutral finger, the electrons will jump off onto the electroscope, thus making the electroscope negative. So this is charging negatively with induction. And so those are the big four experiments that you're doing today. Today you're going to have, yes?
So like, are you pulling the positive rod away, like when you touch it with your finger? Like, what keeps the negative from jumping to the positive rod?
At this part? So when my finger touches, I've got an overall neutral part. I got huge reservoirs of positive and negative charge. And I touch a region that is devoid of electrons. So in that particular interaction, the electrons jump off the finger and go onto the electroscope, and then I pull away. The net effect is this one gains electrons, this one loses.
So you're pulling that rod away too?
Yes. So really what happens, it's kind of a delicate thing. You get in close, and then the moment you touch it, probably I would pull away my finger first, and then you just pull it away. And then when you've got both of them away, and you've really charged that thing well, that gold sheet will come out at like 60 to 80 degrees. If it's a weak charge, 10, 20 degrees. But it still proves the point. So the last part of this that you guys have to know for the lab is you get an electroscope that is just charged. You could charge it negatively, positively, it doesn't matter. So let's say that our electroscope is negatively charged. So there's an extreme excess of electrons. And what you do is you take a match and you light it. And then what you notice is with time, the leaf will fall. and join with the main rod and become neutral. What is happening is that we have to understand what a flame is. A flame is a plasma. And a plasma is just a big bunch of hot gas with a whole bunch of ions. This thing is just burning. And so with burning, you're creating ions that are positive and negative. And what happens is that the positive ions are created and they see that electroscope. And so they move over and make contact with the electroscope. The negative charges see the negatively charged part of the electroscope and they move away. And gradually, those big positive charges, and really they're just atoms that are positive, have deficits of electrons, make contact with the electroscope, and then you leave with both things are flat. So this will balance out an electroscope and neutralize it. The other best way to neutralize an electroscope is just to take your fingers and then just pinch the top. And you can think of your body as just a big reservoir of electrons. And so it will balance out whatever charge you have on this thing. But that's the first lab. And in terms of your bottom line, which is it going to be on the test? Multiple choice, yeah. It'll ask you, like, you rub ebonite rod with rabbit fur. What happens to the electrons? The electrons go from the rod to the fur, from the fur to the rod. Or when you rub rabbit fur on an ebonite rod, the protons move from the fur to the rod. True or false? The positive charges move from the rod to the fur. It's false. Why is it false? Positive charges don't move. Now, the only thing that does move is the plasma, but that's a special case. In terms of the electroscope and the rabbit fur and the rods, the positive charges are not moving. So that's the first part. Now we get to start using equations. In a lot of what we do in the beginning is it's a little bit of a review while we add some electric fields or electrostatic stuff. But in the beginning, I really need you guys to know how to review vector addition. And review 1D and 2D motion. All of these lectures from the summer have been posted onto YouTube. And really what I'm doing is I'm just treating this class like this group of students is the same as the June group of students, so that if you were to look at those lectures that we did in June, you'll be able to easily follow what we're doing now. In 214, we first are introduced to Coulomb's law. And Coulomb's law determines the force on a charge from another charge or group of other charges. So Coulomb's law determines magnitude only. And when I write, the first thing I'm going to do before I introduce the equation is we're just going to draw charges and then show how it affects things. If I write this, you can tell that it's F, so it's a force. This implies that it is a vector, which means that we have a magnitude and direction. And then the 1, 2 needs to be read as on 1 by 2. So to read this out in English, this is the force vector on 1 by 2. So if I wrote F3, 5, this is the force vector on 3 by 5. Now let's do some, let's just draw some pictures. This is charge 1. This is charge 2. They are unlike charges, so they repulse or attract. They attract. So the force on 1 by 2 is to the right because it's attracted to that positive charge. The force on 2 by 1 is to the left. So it's attracted. Both are attracted. If we had 2 negative charges, same 1, same 2, they repulse. And we get that. Coulomb's law determines the magnitude of the force. Trig determines trig and I would say placement determines direction. So the two charges are all on the same number line. So just looking at this, what is your absolute angle for F12 here? 0 degrees. Why? Because it's going pure right. What's the absolute angle for F21?
180.
It's 180. Which one, F12 or F21, has a negative x quantity? F21, because it's going left. So you're going to have to remember all that vector stuff that we did. Oh no, we're building up on previous bits of information. If I had, let's set something else up. Let's say I have a negative charge and a positive charge, 1 and 2. F21 is in this direction, F1, 2 is in that direction because they're attracted. One of the things that you have to pay attention to is that when you determine the all these direction stuff, let's say the origin was placed here, so that physically that was in this fourth quadrant and that was in the third quadrant. What can I say about what quadrant vector is F21? It is not fourth. It is third. The location of the object is in the fourth quadrant. That's a geographic location. What I asked for is the force vector force onto by 1? What vector is that? It's a third quadrant. How do I know it's a third quadrant? Because it's going down and to the left. Remember this about scalar magnitude only. 3 kilograms, 10 seconds, a dozen eggs. Those are magnitudes. Vectors are magnitude and direction only. So you could have 4 meters at 30 degrees. You can have 7 meters per second at 220 degrees. But let me ask you a question. Do vectors have information about their location? They have magnitude and they have direction. There is no information about location, physical location. 4 meters at 30 degrees can be that vector. 4 meters at 30 degrees can be that vector as well. The physical location of the vector does not determine what direction that vector goes into. So even though physically that charge is in the fourth quadrant, the vector is down and to the left. Therefore, the vector is a third quadrant vector. This vector is up and to the right. Therefore, it's a first. Yes. Vectors are not affected by its location. So when we start adding these vectors up, we're not really interested in where these particles are. We're more interested in where these particles are relative to each other. Now, as an example, we've done the easy ones. These are the ones where when we took our vector addition test problems and final problems, one of the things that we did is one of the vectors was an instant conversion vector. These are instant conversion vectors. They are all multiples of 90 degrees, 0, 90, 180, 270. When you see a vector that's lying on the axis, either vertically or horizontally, 3 meters at 0 degrees should be instantly converted to 3x hat meters. You should just know this. In the test, we're going to be adding not force vectors. Well, we're going to be adding force vectors due to charges. And so we're building up to this. Let's say that this coordinate was 4, -1, and this coordinate down here was -3, -6. And we need some geographic or some geometric information. The first is, well, what's the distance between the two? Well, all you have to do is calculate the difference, the change in x, and the change in y. And then you've got the hypotenuse. This hypotenuse we're going to call r. So r is the square root of delta x squared plus delta y squared. You're just going to need to know the distances between the two. So I'm going from -3 to 4 for my x, 7. I go from -6 to -1, or 5. So 35 plus 25 is 60, and the square root of 60 is 7.75. And we'll just say, excuse me?
7 squared 49, not 35.
Oh, blah. Yeah. All right, rule number 1, don't trust old men. There was one time, oh God, I was so frustrated. There was a time where I sat in front of the class and could not figure out why. I thought it was obvious. -1 times -1 is -1. Why can't my class figure this out? And then a part of my brain was like, excuse me, let's come back. I need to talk to you. So always double check my numbers. Yes, so I get 8.6, correct? To the one who corrected me?
I don't know, I just remember.
That's what I got.
Okay, good. All right. We don't have, there was a student in my 214 in spring. I called her calculator girl because she just sat there. She took notes, but she was double checking everything. So it was like, it was her superpower. I was amazed. Now, the other thing that we look at this is, I want to know that angle, and that's going to be a reference angle, and I want to know that angle, because that's also a reference angle. And really what you do when you use these angles, you treat those points as mini origins. To work with the angles, you treat them as mini origins. And this reference angle here is going to be equal to that reference angle there. So theta r is inverse tan of opposite over adjacent. And I'm only going to use the magnitudes. When we do vectors and vector additions, when we determine our reference angles, we are going to use the absolute values of the changes in x and y. It's the way that we do things. Take a look at the old lectures to see why. And this is the inverse tan of 5 over 7. And now I started to doubt myself on everything. 35.5 degrees. So So that's that reference angle there, and that is that reference angle there. Okay. And really what I've done is I've kind of set up this problem, because what I'm going to do is I'm going to write out the problem. At 4,1 meters is a negative 6 millicoulomb charge. At -3, -6 meters is a positive 4 millicoulomb charge. What is F12 and F21? So charge 1 is down. I don't think we ever, yeah. Charge 1 is that lower left charge. Charge 2 is the upper right. Now we get to finally introduce what Coulomb's law is. Coulomb's law is that the magnitude of the force on 1 by 2 is K big Q1 big Q2 over R squared. And this is Coulomb's law. That's the big guy. Coulomb's law is this constant K. Forget it's 9 times 10 to the 9th. I believe it is Newton's meters squared over Coulomb squared. And those Q's, and I guess we need to introduce, well, what's a Coulomb anyway? Q1 and Q2 are the magnitudes of Q1 and Q2. First things first. We know that force is a Newton and R is a distance, which is measured in meters. For charge, the symbol we use is C, and that means a Coulomb. Charges are measured in coulombs. Charge of an electron, 1.6 times 10 to the negative 19. So when you have charge typically comes very small. Millicoulomb charges are pretty big. If you had a coulomb of charge, you got a lot of charge. But I'm not a big fan of numbers. As long as the numbers work out, I'm happy. So those are some fundamental units. Q is a magnitude, therefore always positive. Q can be positive or negative. So if you see that big Q wandering around, you've got the big positive charges. If you got a little q, then you're going to have to pay attention to the sign of the charge. That means Coulomb's law will always give a positive value. Coulomb's law will always give a positive value. Coulomb's law will always give a positive value. Now, if I break into a brief moment of being your private tutor, I would ask, seriously, Dr. Eschenberg said that like 3 times in a row? Yeah, he did. Then he means business about that. If I ask you to use Coulomb's law to find a force between 2 particles and you give me a negative answer, that's when the big red pen comes out and I just start hunting for points. Coulomb's. Now, the force that we determine on this can't, and when we figured this out in terms of vectors, it's going to have negative components, but the initial number that we get for the magnitude is always going to be negative. The thing that, when we look at this, F12 is K Q1 Q2 over R squared, and this is from 1 to 2. F21 is K Q2 Q1 over R21. And when you look at these, the distance from 1 to 2 is the same as the distance from 2 to 1. The magnitude of charge 1 times magnitude of charge 2 will give you the same answer as charge 2 times magnitude of charge 1. So these are equal. You don't have to figure it out a second time because you're just recomputing the same numbers. There's no point. I am like you. A lot of people call it lazy. I call it efficient. There's just no point in recalculating it the second time when you're just going to get the same answer. So let's get this answer. F12, 9 times 10 to the 9th, 6 times 10 to the negative 3, 4 times 10 to the negative 3. Notice they're all positive. R12 is 8.6. And so we're left with a magnitude so 2920.5 newtons. During these intermediate values, I carry out 4 or 5 sig figs just to minimize or to reduce the amount of bit rot. To those of you who did not take Summer 213, my faith in alphabet soup being superior to plug and chug is still in full effect. It did not go away. So we're doing things, once we get everything introduced, we're still doing alphabet soup. So that's the force. There's a 2900, yes?
So they're to the negative third because they're millicoulombs?
Correct. So you're going to have to remember, let's now pop quiz. Millis 10 to the negative 3. What's 10 to the negative 6? Micro. What's 10 to the negative 9? Nano. What's 10 to the 3? Kilo. What's 10 to the 6? Mega. What's 10 to the 9? Gig. What did you say? No, that's the other way. Giga, and then for completeness, because it just bothers me that we don't mention it, what's after giga?
Tera.
Tera, which is 10 to the 12. Or 10 to the 9. So having an ability, you gotta keep all that stuff. When you see me give these things in milli, you immediately change to coulombs. So millicoulombs, you're gonna have to change that to coulombs. If I give millimeters or kilometers or centimeters, you're gonna have to convert that to meters. And why is that? It's because the constant K, 9 times 10 to the 9th, uses newtons, meters, and coulombs. So unless you want to start converting that constant, just convert the others and you'll be fine. So we've got the magnitude, 2920.5. I'm just going to say, I'm tired. I'm just going to write 2920. The numbers don't matter. It's the technique right now that I'm primarily interested in. So we found these angles, and really what we're going to do is that force is F on 1 by 2 vector. That is a force on 2 by 1 vector. F12 is up and to the right. F12 is a what quadrant vector? It's first. Even though it's located in the third, when I say F12, I'm looking for the direction of that vector, not location. So this becomes F12 is equal to 2920 newtons at 35 degrees. I'm just shaving stuff off because I don't care. But you could say 2920.5 at 35.5 degrees for your accurate answer. So that's the force vector using absolute values on this. Now looking at F21, we're going to do it two different ways. What are those directions? They're opposite. So you can think of it as when you calculate vectors for equilibrance. You just add 180 degrees to it. So F21 is 2920 newtons at 215 degrees. The other way that you can do it is that angle's 35, that angle's 35. The absolute angle is that. And what do? You take, for a third quadrant angle, you take your reference angle and add 180 to it. And then you're right back into the situation. So those are the vectors for 2 points and using Coulomb's law to determine it. So if you have positive charge down here and a negative charge up here, each of them will be pushing towards or pulling towards each other with a force of 2,920 newtons, which is a lot, at some certain directions. Now, not everything is going to be this easy. Typically, the way that we do things for the test is I will set up a third charge and just so that I want to keep all the angles right. Q1, Q2, Q3. Q1 is positive 4 millicoulombs at the coordinates -3, -6. Charge 2 is -6 millicoulombs at 4.1 meters. And then charge 3 I'm going to give as hold on, I want to get this the right way. I'm going to do negative 8 millicoulombs at negative 3, 4 meters. And the question is, what is the net force on Q1? So what is the net force on Q1? The net force, the sum of the forces on charge 1 is going to be hold on, how do I get this? So the force on 1, the total force on 1, is the sum of 2 vectors. This charge is pulling that charge up and to the right. I've added a third charge, which is up here, and it is negative 8 millicoulombs at negative 3, 4. It's a negative charge. Oh, that looks like a G. That's not a G. That's a C. It's a negative charge. This is a positive charge. So it is pulling that up. And this is force on 1 by 3. So a couple of comments. This is, what I'm looking for is the sum of those 2 forces. Now, focusing only on that first charge, to find its sum, you use that first force vector, and then you use the second vector. And that is the tip to tail method. So the sum of these force vectors is going to be a first quadrant vector, most likely. You can even do the parallelogram method. Go second vector first, and then the first vector second, and again you end up at the same location. So when summing the forces, you are only using the forces acting on the charge being studied. Notice when we are looking at these the question was, what is the net force on that charge 1? I did not ask anything about how is charge 2 affecting charge 3 and how is charge 3 affecting charge 2. I made no mention of that. So all you care about, the forces on 1, the charge can't affect itself. So you're only concerned about charge 2's effect on 1 and charge 3's effect on 1 as well. I do not care about how 3 and 2 are getting along or hate each other. This question is only about 1. Now we have F12. F12 we got earlier. I have it down. Yeah. It is 2920 newtons at 35 degrees. That's F12. We've got to find F13, and we have to find the magnitude of F13. So F13, using Coulomb's law, is that K is 9 times 10 to the 9th. Q1 is 4 times 10 to the negative 3. Q3 is 8 times 10 to the negative 3. Remember, Coulomb's law only uses magnitudes of the charges to get that positive answer. And then R13, and this is where I make things easier. One of the charges, the geometric arrangement, this charge is directly over that charge. They both have the same x coordinate, negative 3. So the total distance is -6 to 4, or 10 meters. So this becomes 10 squared. And that force gives me $2880. A nice, good whole number, as it should be. 2,880 newtons. Now that is a positive charge, that is a negative charge, so the force is going to be straight y-axis. So what is this force vector in polar notation? Now, for those of you who took 213 in the spring and the fall, I forgive you. But for those of you who took it in June, I expect your neurons to be at full velocity, unless you destroyed them in a mere 2 days. What did you do? A couple of cases of vodka will have to really to have an effect on like that quickly. Give me the force vector on 1 by charge 3 in polar notation. Yes.
2,880 newtons at 90.
Correct. It's acting in a pure positive y-axis. It's going straight up. All you had to do was look at, when I went from there to there, all I did was change the y coordinate, not the x. So this has to be a pure positive y vector. So in vector notation, it's 2880 y hat newtons, or 2880 newtons at 90 degrees. I promise you, one of the vectors that you set up in your vector addition problem on test 1 will be an instant conversion vector. All you have to do is get that front end going. So now we have 2920 at 35 added to 2880 at 90. All problem 1 is from test 1 for 214 is a simple vector addition problem like you did in test 1 for 213, but with Coulomb's law sitting in the front. And so you have to determine the magnitude of the force, and you're going to have to determine the direction of the force. I'm not going to give those force vectors to you directly like I did in 213. You're going to have to make them. And the homework is a great source of problems to do or to work with. Now it's vector addition. We're all familiar with vector addition. That's already converted into component. 2920 at 35 is a first quadrant. First quadrant reference angles are the same as their absolute angles. So F12y is F12 sine theta r, which means it is 2920 sine of 35. F12x is F12 cosine of theta r, which is 2920 cosine of 35. And this gives me 1674.8 and this gives me 2391.9. So F13 is 0 in the x and positive 2880 y hat. Oh no, this is F12. No, I take that back, F13. F12 is what we've just been playing with. It is 2391.9 x hat plus 1674.8 y hat. Remember the 3 steps of adding vectors. You break them. You use basic trig to take those polar vectors and convert them into component vectors. Part 2, you add them. You take those vectors and you add your x's and y's to y's. You don't mix x's and y's together. So this becomes 2391.9 x hat plus 4554.8 y hat. And this is the sum of the force vectors on object 1. So in 213, we were using forces as like the force table. You had all those strings pulling that ring with the thingy-me-bob in the middle, and you got to keep the ring around it. In this particular case, the forces are not coming from weights pulling on strings. The forces are coming from charges interacting with each other. The sum of the forces is this. This is the answer in component notation. I know. The 213 veterans from June can handle 2-hour lectures. You guys, we've just passed the hour 23 mark, so we still have 36 minutes to go. Or wait, no, we got less than that. We end at 11:50, I promise, and we don't go over. So the last part, if I gave you that and I said, give me the answer in polar notation, all of you should be able to do this real quick. You draw out your triangle. It's obviously a first quadrant vector. Why? They're both positive. So my reference angle is going to equal the absolute angle, and the absolute angle should be between what numbers? 0 and 90. So that reference angle is the absolute angle. So we don't have to play any weird games with the signs. That's why I love first quadrant vectors so much. 4, 5, 5, 4.8, 2, 3, 9, 1.9. So I get 62.3 degrees. And that is the angle of this vector. The magnitude, all you have to do is you just take f1x squared plus f1y squared, and that is the magnitude of f sub 1. This becomes 2391.9 squared plus 4554.8 squared. And I get and square root that. And I get 5144.6. So you could round this stuff off. So your final answer as a vector will be 5145 newtons at 62.3 degrees. Now, one of the things about just adding vectors with these charges, there are a lot of places where I was rounding. And one of the things that the graders will be prepared for are looking at, knowing that you're going to round a couple of times. So the 51, if you get 5148 at 61 degrees, they're not going to throw the red pin at you. If you got 21 newtons at 340 degrees, then they know something just weird went on, and so they'll come at you and take a look. So that's, I know we're covering a lot of information. The big difference between the fall and the spring semesters versus now is when you took my course in the fall and the spring, I'd give you the first problem set, you got a week to work on it and everything is fine. Now I give you the problem set, and a week from now, well actually it's a week and a half because of the holidays, we're gonna have a test. So things move quickly. There are tons of examples that I've done. Just go on YouTube, look at those videos, look at this video, go over and over it again and see what I've done. Moving on. Coulomb's law . You have two charges, and the question is, what's the force on those charges? There is something called electric field. And the electric field says, given a charge Q, you're at a particular point at a particular distance, tell me about that point. and the way that I kind of, oh, I didn't bring my tennis balls. So if I have a charge right here and I have another charge here, they're going to feel forces. If I bring them closer together, they're going to feel a stronger force. What's changed? What's the difference between a point here next to a single charge acting by itself and a point that's right next to the charge? And that is the electric field, where Coulomb's law is the force KQ1 Q2 over R squared. The electric field is KQ over R squared. There's no second Q. You're studying the point, not the effect of that charge on another charge at that point. You're just studying the quality. And once again, this uses Q. So E will be positive. It will always be positive. This is something that we do not go around. It will always be positive. If I say determine the E field at that particular point, not as a vector, that answer better be positive. If I ask for use Coulomb's law to find the force as a non-vector, it better be positive. So if you have a simple point here, like 5 millicoulombs, and you're at a particular distance out there, and let's say that R was 2 meters, the electric field at that point has a particular quantity. E equals KQ over R squared, 9 times 10 to the 9th, 5 times 10 to the negative 3, and then R is 2. And I get, ooh, big number, 3, 6, 7. 1.125 times 10 to the 7th newtons per coulomb. Units of electric field are measured in newtons per coulomb. And so you can figure it out. Now, because of where this charge is, the E field vector here and the E field, E magnitude there and 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 there, if they're all at the same distance from the positive charge, they have the same electric field magnitude. Their E field vectors are different. The thing about an E field vector is the E field vector line shows in what direction a positive charge experiences a force when placed at that point. So if you put a positive charge there, it would go up and to the left. If you placed a positive charge there, it would go to the left. If you placed a positive charge here, it would move down. And what you find out is that these electric field lines, positive charges have outward bound E field lines. So if I simply drew a positive charge and so on, those E field lines all radiate outward, regardless of your location. If I'm here, this is a pure positive y hat vector. If I'm down here, it's a pure negative y hat vector. So this E field vector is based on distance from charge and its positioning, or its position with regards to the charge itself. So you know that the positive charges are radiating, and this is one of the reasons why the E field and Coulomb's law, we make them magnitudes, because the magnitude here and there are the same, but they are in different directions. And so for the second part, to determine the vector direction, you're going to have to use a little bit of logic and observation. Charges over here, E field to the left, positive or negative X. Charge over here, positive X. Charge over here, negative Y. Charge over here, negative Y, negative X. So you're going to have to pay attention to your position with respect to where that charge is. If you have a negative charge, if you put a positive charge here, it will go towards the negative charge. So the E field lines show where a positive charge would go if it was released at that particular point. And because it's a negative charge as the source, the positive charges would all be drawn inward. So whereas positive charges radiate out, the negative charges radiate in. They draw in. So if we had, now it brings up an interesting idea. If we had a positive charge and we know for a fact that its E field lines are like this, and I put a negative charge right there on the line, would the negative charge move with the E field line or against the E field line? It sees the positive charge to the left, so that negative charge would be attracted to it. It will feel a force to the left. So this one feels a force in that direction. If it was a negative charge, its E field lines radiate inward. So if I again put a negative charge there, it will experience a force away from the negative charges. Positive field forces parallel to the E field vector. Negative field forces anti-parallel. And I use this word, we've probably forgotten. Parallel, when we all know parallel lines from geometry in high school. Parallel lines just mean side by side. But in physics, we add an extra layer to it. Parallel means that the vectors are going in the same direction and they're side by side. Anti-parallel means that the vectors are still, they have parallel qualities about them, but the vectors are going in opposite directions, not parallel. So the big thing that we have to understand is positive charges feel forces that go with the E field lines. Negative charges feel forces that are opposite of their E field lines, of the E field lines given to them. So a couple of just hypotheticals. In a way that so for charges, we have the further away you get from a charge, the weaker the E field is going to be, because the E field is K Q over R squared. If I double the distance from a charge, the E field gets cut by a factor of what? If I double the distance, the E field gets cut by a factor of what? 4. Because if I double it, it's squared. 2 squared is the 4. We're going to be dealing with, coming up soon, capacitors. And we'll talk more about capacitors at a later time. But what I want to get to is introduce the idea of capacitors, and within this region we can set up so that the E field vector is homogeneous. It's always in the same direction, it's always with the same magnitude. And so in physics, we can set up environments like this. One of the best examples is a capacitor. And so in our hypothetical world, in this capacitor, from your vantage point, the electric field lines go from left to right. Let's just assume that the left side of the room is a plate. We're physically inside a capacitor. On the other side is another plate. And what I do is, I don't want to tear up those. I'll tear up a blank sheet. So there's my room of electric field. It is uniform. All the electric fields are from left to right with the same magnitude. And I put a positive charge right there. That piece of paper is a positive charge. Which way is that thing going to move? It's a positive charge. So it experiences forces that are parallel with the E field. So parallel means it experiences a force to the right. So it will, what it will do is it will start and then accelerate, 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 and eventually hit. If I had let's say that this piece of paper was a negative charge, if I put it there, would it move? No. It would experience a force to the left, but since it's already on the plate, it's not going to move. It just won't budge. I have to put the negative charge over here. So positive charges will want to go that direction. Negative charges will want to go in that direction. And this is where Coulomb's law and the electric field lines are related to, that the force on a charge, actually let's just keep magnitudes here, is charge times that electric field. If you have a charge and you know what electric field you have, you can determine the force. If the charge was, let's just play with 3 nanocoulomb charge, and the electric field was 20 newtons per coulomb, the force on that charge is 3 times 10 to the negative 9 times 20, or 6 times 10 to the negative 8 newtons. That the charge, you can determine the amount of force on a charge. And one of the things that we do by playing with capacitors is that then we don't have to deal with all those bizarre vector addition, because if it's in different places, it makes things way more complex. This is more simple. Now, what's really interesting is that charges do not have, we got 4 minutes. Charges do not have, or they do have mass. So let's say that this charge had a mass of 2 grams. If the electric field was going in this direction, it would feel a force in that direction, and it would experience an acceleration in that direction. So what law that we know about makes a relationship between a force and its acceleration? Newton's second law, F equals ma. So F is equal to ma, so the acceleration is F divided by m. So the force is 6 times 10 to the negative 8. The mass is 2 times 10 to the negative 3. And it now experiences an acceleration of 3 times 10 to the negative 5 meters per second per second. And now that we've made a relationship that F is equal to QE and F is equal to MA. So A can be equal to QE over M. And when we're dealing with this stuff, the electric field lines are going to be all nice. And if you've got an acceleration in a uniform electric field, now I can do fun things like use my position equation and my velocity equation and play all sorts of fun problems with this. And this will be what I'll close on. In 213, if I had a charge, well, let's just say I just had a simple mass, and I drop it. I say, well, why didn't it move to the side? And your answer was, or the answer that I beat into you, was that there was no horizontal acceleration. It was all just in the y-axis. And I said, there will be a day where there will be a horizontal acceleration. Because if this is a charge with mass, gravity is providing the force in the vertical, and I'll have set up an electric field that is acting in the horizontal. So if there is an E field in this room and gravity, when I drop it, it won't just fall straight down, it will fall to the side. And so that opens up a whole new class of problems. That's it. See you tomorrow. If you need to talk to me about lab, you can see me right now or in my office.